Swayam Prabha. Digital India. Educated India.
Hello and welcome back. This is the second lecture on special relativity. In the last lecture, we saw that to translate observations of the physical world between different observers, we need to establish a dictionary. Now, establishing this dictionary is always possible for any sets of observers. However, for a special class of observers, so-called inertial observers, Newton's laws always appear to be valid. These observers appear to be moving with respect to each other at a constant velocity. That is, they have uniform motion with a constant speed as well as constant direction with respect to each other. More importantly, there appears to be no preferred inertial observer. All of these observers are equivalent. That is, there is no preferred rest frame of the universe. This idea seemed to fit quite well with this Newtonian way of thinking. However, towards the end of the 19th century, it became quite apparent that this transformation, this dictionary of Galilean relativity, which appeared to be consistent with Newton's laws, did not fit in with Maxwell's equations. This led to a paradox, and we will see today how Einstein thought about this paradox and puzzled over it. So here's the plan for today. We'll begin by talking about the relationship between Maxwell's equations and Galilean relativity, and we'll see exactly where the conflict is between Maxwell's equations and Galilean relativity. Attempts to resolve this conflict resulted in an experimental test which was the Michelson-Morley experiment. And we will see that the results of the Michelson-Morley experiment were quite counterintuitive to what physicists expected at the time. This led to a paradox where Einstein began to puzzle over this result, or what was a null result of the Michelson-Morley experiment. And we will see his thought process for how he began to resolve this paradox. Observers, for consistency with what we're going to do later, so we'll call this first observer, observer S, and this observer as S prime. And what we saw is, if the distance between these two origins is changing with time, these observers are moving with respect to each other at a constant velocity. So this distance is, let's say, some v relative times time. Time is measured either by the first observer or the second observer. Okay, so now if you take these two different observers and you look at any particle and you ask what its speed is, so let's say the speed as measured by observer S is, and let's write the speed here as Vs. This is the speed measured by observer S. Now the speed as measured by observer S prime would be Vs prime, and the relationship between these two would be Vs prime would be Vs minus Vr. Okay, if these are vectors, then you would take into account appropriate vector signs. What this tells me is that since the observer S prime is moving to the right, this object should appear to be moving slower with respect to observer S prime. So now here's the conflict, or here's the worry, which is if I look at Maxwell's equations, it's telling me that there is some speed c with which light waves travel. But from the principle of Galilean relativity, so this here is from Maxwell's equations. And this is from Galilean relativity, which is consistent with Newton's laws. We see that all speeds and all velocities are observer dependent. So if the velocity as measured by one observer is Vs, the velocity as measured by the second observer will be Vs prime. And for simplicity, let's just suppose that everything is moving along one direction, let's say the x direction. So what this means is, if I have a particular observer, S, who is, let's say, at rest, they see light moving to the right with a speed c, and you now have a different observer with S prime, who is moving to the right at a speed vr relative to the first observer. What you would expect is that the speed of light as seen by this second observer would be some c prime, which would be related to the original speed by c minus vr. Okay, that is, they would see a reduced speed for the speed of light. Now, in Galilean relativity, we have no way to pick a preferred observer. At least Newton's laws don't allow us to pick a preferred observer. Okay, so the question is, Maxwell's equations tell us that there is a speed c. So Maxwell's equations tell us that there must be a preferred observer or rest frame with respect to which the speed of light is that constant c. Okay, at least this was the thinking at the time. And therefore Galilean relativity holds. Okay, so the assumption is Galilean relativity holds, and different observers who are moving at different speeds will see a different speed for light. But there is one particular observer who measures the speed of light to be c, which is the speed in Maxwell's equations, and they become that preferred observer. Okay, so Maxwell's equations tell us that there is some particular reference frame or some particular inertial observer who is the preferred inertial observer. So this reference frame, this preferred reference frame, was called the ether. So the thinking towards the end of the 19th century was that there is a preferred rest frame, this ether, and there must be a way to figure out what this reference frame is. So by that we mean the Earth is moving around the sun, and of course the sun is moving around the center of the galaxy. So since the Earth is moving, we must be moving with respect to this ether, this preferred reference frame. And at different times of the year, we would be moving in a different direction with respect to this preferred reference frame or this ether. Okay, so at a later point in the year, assuming that the sun hasn't changed its position significantly, we would be over here, and we would be moving in the opposite direction with respect to the ether. So at different times of the year, okay, we would be moving in different directions. So for simplicity, let's just assume that the rest frame of the sun is this preferred reference frame. And you can clearly see that at different times of the year, we would be moving in different directions with respect to this ether. Now, people tried to conceive of an experiment which would detect the motion of the Earth through the ether. Okay? And the experiment which was designed to detect this motion of the Earth relative to the ether, that is to detect the preferred rest frame, was called the Michelson-Morley experiment. So here's the idea for the Michelson-Morley experiment. Let's start by viewing the world from this preferred rest frame, this ether rest frame. Then the Earth at any time is moving with a velocity v Earth. We don't know what this velocity is because we don't know what the rest frame of this ether is. But it's moving with some speed relative to this ether. And that speed is not constant, clearly, because at different times of the year, we are at different positions around the sun, so therefore we're definitely not at rest with respect to this ether. At least at all points in the year, we cannot be at rest with respect to this ether. And now let's imagine that we consider light rays, again in the reference frame of the ether. So in the ether reference frame, let's take light, which is moving in different directions. Okay, so according to the conjecture at the time, in the ether rest frame, the light traveling in every direction has a speed c. Okay, no matter which direction you look, the speed should be c. But what that means is, according to the principle of Galilean relativity, if we took an observer moving along with the Earth, that observer should measure different speeds for the speed of light depending on which direction the light beam was going. That is, if the observer moving along with the Earth were to ask what is the speed of this light beam, since they're moving along with that light beam, they would measure the speed of this light beam to be lower by this amount, c minus VE. Similarly, if they asked about this light beam, they would measure a higher speed because they are moving away from this light beam, so they would measure a speed c plus VE in this direction. Okay? So, different directions of light beams would have different velocities as measured by an observer on the surface of the Earth. So the idea of the Michelson-Morley experiment was to try to take measurements, or effectively measure, the differences between the speed of light in different directions. That is, try to measure the speed of light as seen by an observer on the Earth in one direction and another direction, maybe let's say an orthogonal direction. And the speed of light in these two directions should appear to be different to an observer on the Earth. An observer on Earth should measure different speeds of light in different directions. So in principle, if you measured the speed of light with respect to the Earth in many different directions, Okay, so you made many different observations of this. You know what the speed is in the ether frame. Then you could use that to determine the relative velocity between the Earth's frame and the ether frame. So using these many different observations, okay, making many different observations of the velocity of light in the Earth reference frame, and knowing the speed in the ether frame allows you to determine the relative velocity between the Earth's frame and the ether frame. So this would be a detection of what we would call ether drift, that is our motion with respect to the ether. Okay, so this experiment was designed to measure the difference between the speed of light in different directions, and the result would be a detection of the ether drift. So let's see the setup for this experiment. So the idea for this experiment was to use what is called an interferometer. So you set up a light source which emits light which is coherent, that is, it has a particular wavelength lambda, which is the peak between the distance between two peaks of the electromagnetic wave as it propagates to the right. And in the way you set up a beam splitter, and what this beam splitter does is it reflects half the light in this direction and it transmits half the light in this direction. Okay, and the light beams travel some distance L before they encounter a mirror. So this mirror is placed at some distance L, away, and this is a reflecting surface, and similarly there's another mirror over here. So the light beams travel some distance and then they get reflected back, travel some distance and get reflected back, and you arrange it in such a way that effectively this length L is the same as this length L over here. So the light beams travel exactly the same length. They travel a length 2L between going forwards and backwards. They travel a distance of 2L. And then you recombine those two beams. And since light is a wave, these two beams should interfere with each other. And what you do is you now try to detect. Okay, so you put a detector here. And you try to measure the interference pattern between these two light beams. Okay, so let's examine that setup again. You send light beams, a single light beam to the right. It's a coherent light beam with a single wavelength lambda, and part of it is split in such a way that it moves to the right. Another part is sent upwards, and both these different split light beams now, they travel the same path length. Okay, then they're made to recombine, and then you detect their interference in a detector. Now, if they've traveled exactly the same path length, now the speed of the light, okay, in this direction, let's suppose, is v1. But if the speed in this direction is v2, which is different from v1 because we are drifting with respect to the ether, light should be traveling to the right with some speed v1 and upwards with a speed v2. And these speeds v1 and v2 should not be the same. Okay. Otherwise that would be inconsistent with the idea of Galilean relativity applied to light. So now the number, you can count the number of so you can determine now what the phase difference would be between these two different light beams when they are recombined. Okay, once they recombine, they do exactly the same thing, so they're not going to pick up any phase difference over here. The phase difference just comes from the fact that these light beams had different speeds when they were moving in this direction to the right and this direction upwards. So if you ask what is the phase shift of the light of light beam 1, which moves to the right and comes back, the total phase shift, the change in phase, would be proportional to the path length traveled divided by the speed of the light beam as it went to the right and back. Similarly, for light beam 2, the total change in phase as it goes up and comes back down would be, again, the path length divided by the speed. Okay, sorry, proportional to. So you can show that that proportionality constant here would depend on a property of the light beam itself, which would be the frequency of the light beam. So that proportionality constant would be omega, where omega is the frequency of this light beam that you originally transmitted. Okay, so this frequency is the same. This frequency does not change for the light beam which goes this way as well as the that goes this way, because the frequency determines the vibrations in time. Okay, and that vibration in time is what's sourcing the light beam that's moving to the right or moving up. So the phase difference that's arising when this light beam moves to the right and when it moves up is arising purely from the fact that the speeds in these two directions are different. Okay, because the path lengths are exactly the same, the frequency of the light in both directions is exactly the same. So the only thing that can create a phase difference is the fact that the speeds of light are different in these different directions. So at your detector, you will detect a phase difference, delta phi, which would be the phase picked up by the first light beam, which moved to the right, minus the phase picked up by the second light beam, which moved up and back down. And that phase difference would be omega times 2L 1 by V1 minus 1 by V2. Okay, so there would be a phase difference just from the fact that the speed in one direction is different from the speed in another direction. So different speeds in different directions would create an interference pattern. Okay, So the goal was, if you arrange for these path lengths to be the same, can you detect such an interference pattern? I just want to take a minute to show you how to get this phase difference between two light beams.